All right, so I am recording now. I'm going to record the answers to problem set number 13, and then I have some other example problems that I'll do as well, just for fun to help you out, and they probably also will help you out on the next problem set that is due next Monday. All right, so I'm going to share my screen, well, my camera actually. Okay, so here's problem set number 13 that you already submitted. And we actually talked about most of it last week. So this probably is not a big surprise. It shouldn't be any big surprise. You did this last week, half you on Monday, half of you on Wednesday. You put the compass around here after you put a bar magnet here, and then you connected the lines, and the lines should have looked something kind of like this. And last week we talked about some rules for drawing lines of magnetic flux. We talked about how they always go from north to south. So one thing I was looking for when you submitted Lab 13, I've got to see these arrows going from north to south. So at least one arrow on each line. Sometimes I put two just for clarity, but something like this. Also, they should never intersect. And lastly, for a denser, for a stronger magnetic field, the lines should be denser. Those are the three rules for drawing lines of magnetic flux. And then for number 2, we had a coil of wire. So your coil might have looked kind of like that. And then you applied a voltage. You didn't have to draw in this voltage source, but effectively this is what we're doing. We've got a positive side over here and a negative side over there, or vice versa. And we plotted the magnetic field around here. And what you should have seen is basically the exact same thing as in problem number 1. So you should have seen a magnetic field that goes kind of like this. And what I told you to do in class last week was to just pick one. Now you know, after watching the videos on Monday, now you know which way the magnetic field is, but we didn't know that last week, so I just told you to pick one side and call that the north side, so maybe that would be north, that south. And so that being the case, the magnetic field goes from north to south. So once again, I'm looking for those arrows on the lines of magnetic flux. Number 3 is the last one here. It's the only one that we didn't do or really talk about very much in class last week. But the same rules apply. You still got to draw lines of magnetic flux. They got to go from north to south. They can't intersect. Those are basically the rules. So, I mean, they're going to look something like this. I'll draw the arrows in a little bit, but they're going to go kind of like this. Kind of like that. And then all of them are going from the north, the various north poles, to the south pole. So your arrows should look something kind of like this. Yep, something like that. Those are your lines of magnetic flux. I mean, you could draw more in here, but basically that's what they're going to look like. Okay, that was problem set number 13. Are there any questions about problem set 13? I think what I'll do now is I have some review problems that, like I said, would be, I think, helpful to review the material that we talked about on Monday in the videos. And at least one of these will probably help you on the next problem set also. And of course, they're all important for the next quiz and the next exam. So I think maybe what you want to do right now is maybe use either your screen capture, like print screen, or take a picture with your phone of the screen, and that way you have these example problems, and that way we can talk through them, and you'll have a record of them. So in number 1, maybe we'll do it. So I've got 4 of them actually. So I've got 1 and 2 on the first page, and then 3 on another page, and 4 on another page. So maybe we'll just do this 1 page at a time. So I'll show you number 1 and number 2, and then I'll give you a minute, and then we'll actually do 1 and 2, and then we'll flip over to a different page. I'll show you number 3. I'll give you a minute, and then we'll talk about 3, and then same thing with number 4. So here's the first page. Number 1, I want you to draw the magnetic field, which is B. Remember, we talked about that last week. Draw B around this current carrying conductor. So this is just a wire, and I want you to draw the magnetic field around this wire with the understanding that current is going from left to right through this wire. And then number 2, I want you to draw the magnetic field, B, around this electromagnet. So in the real world, we're not just going to use a single wire to create a magnetic field. We're going to create a much stronger magnetic field by wrapping that wire with current going through it around a core material to create an electromagnet, like we talked about in the videos on Monday. So this is good practice from the videos on Monday. So I'll give you about 1 minute here to think about these questions, and in both cases, draw the magnetic fields around these components. I'll give you about 1 minute, and then we'll talk over them. Okay, that's been a minute according to my phone. So let's talk about these. What is the applicable hand rule for the current carrying conductors, for the magnetic field around the current carrying conductors? Well, it's the right hand rule for current carrying conductors. So here's my conductor, and let's say current is going this way. So I put my thumb in the direction of current flow, and I wrap my right hand around it to give me the direction of the magnetic field. So in this case, the current would be going around like this, wrapping around the current carrying conductor like this. So it's going up and back of the conductor and then down in front, up and back of the conductor and down in front. So I need to draw that and show that. So it's going up and back of the conductor, then down in front, and then up and back again. Up and back of the conductor, down in front, and then up and back again. And like we talked about in the video on Monday, there is actually more than one way to show that. So that's one perspective, like from the left. The other way to show the exact same thing, just from a different perspective, is up and back, down in front, and then up and back again. So these are actually showing the same thing. They're both showing the magnetic field going up behind the conductor, down in front of the conductor, and then up and back of the conductor again. So either one of these are correct. Just showing it from a different perspective. Then in number 2, we want to draw the magnetic field around this electromagnet. So I think the way I like to do it is to think about which direction the current is going to flow, and then draw a little magnetic field around the current carrying conductor, and then extrapolate that to the electromagnet. So we're going to have current going in this direction. I'd like to try to draw the current and the magnetic field in different colors. So the current is going left to right in this wire right here. So it's just like we just drew up there. So the current is going up and back, down and front, up and back again. So it looks like this. Here's this wire. I'm wrapping my fingers around it. It looks like that. And then you can kind of imagine taking your fingers and wrapping them around the wire as the wire is wrapping around that core material. And if you imagine wrapping your right hand around the wire and then move your hand to follow that conductor as it's wrapping around this core material, what you'll notice is that your fingers are always going to curl up around the outside of the core material here, up around the outside, and then down through the middle of this core material right here. So the lines of magnetic flux are always going to go up around the outside and then down through the middle. We don't really draw the ones going down through the middle, but it does exist. So here are some lines of magnetic flux, and of course it's symmetrical. There are a couple lines of magnetic flux, and what's the direction? Well, we talked about how it's going up around the outside as the wire is going around. It's going up around the outside of the core and then down through the inside of the core. So the direction looks like this. And now, of course, if we know the direction of the lines of magnetic flux, we know the polarity of this electromagnet, because the lines of magnetic flux always go from north to south. Since they're coming from here, this must be the North Pole, and since they're going to south, this must be the South Pole. All right, but like I said in the video on Monday, you can flip things around in a couple different ways. You can flip the polarity of this electromagnet by flipping the polarity of the applied voltage, just flipping that, or by flipping the way that the coil is wrapped around. So instead of wrapping it around this way, if you wrapped it around the other way, you would flip the polarity of this magnetic field. Try it out. Try it out and use your right-hand rule for current-carrying conductors, and you'll see that it does flip. Okay, that was number 1 and number 2. Number 3 is more about generators that we talked about on Monday. So it's just a simple question: which direction is this generator rotating? So once again, I'll give you a minute here, and then we'll talk about the answer. Okay, it's been a minute, so let's go over this. So here we have a very rudimentary generator. It has a coil of wire with only one turn in it, which is just easier to draw, even though in the real world it would have hundreds, maybe even thousands of turns, like I showed in the hand crank generator. And this thing is rotating. The thing is, we don't know if it's rotating this way, clockwise, or this way, counterclockwise. We don't know which way. We do have a conductor, we have a magnetic field, and if this thing is operating, then we have relative motion because it's going to be spinning one way or the other. All right, and we know it must be spinning because it has current going through it, so it must be operating. So the question is, which way is it rotating? Some type of turbine device, whether it's a wind turbine or a steam turbine or a hydroelectric turbine, some type of turbine, is causing this to spin. So which direction is it causing it to spin? So to answer this, we need to break out our other hand rule that we talked about on Monday. That is the right hand rule for generators. And you'll recall that for the right hand rule for generators, our first finger tells us the direction of the field. This is why it's so important to know that the magnetic field goes from north to south. That's why it's important to know that. The second through fourth fingers give you the direction of current flow, which is a result of the induced voltage in the coil of wire. And your thumb gives you the direction of that conductor, that wire at this point in time. So it's really just a question of making your hand fit with the directions that are given. So the magnetic field is going from right to left here. So my first finger has to point this way. And then I need to make this fit. So I'll apply this to the right-hand wire first, the right side of the armature. So it would look like this. So my field goes from right to left. My second through fourth fingers are pointing out of the page toward the camera, towards you. And that is represented by this arrow, current coming out of the page. And that gives me motion. My thumb is pointing up toward the top of the page. So the motion here is up towards the top of the page. So I would expect the left side of the armature to be doing the opposite, because if this is going up, this is probably going down, get a rotation. But let's double check. So here, my first finger needs to point from right to left, so like this again. And my second through fourth fingers need to point down into the page. That's represented by this current arrow going into the page. So it looks like this. There we go. I had to move my hand around. So it looks like this, and you can see my thumb is pointing down towards the bottom of the page. So the arrow here, as expected, would be going down like that. So at this point in time, this snapshot in time, this wire is going up to the top of the page, this wire is going down towards the bottom of the page, which is because this thing is rotating in this direction, and that is the counterclockwise direction. So it's rotating like this, which is counterclockwise. All right, that was number 3. And the last review or example problem, this one is probably similar to one you might find on the homework tonight. So we're saying we have this generator right here. So it's a really simple generator, only one turn of wire, only one loop in the generator. So it's not very realistic, but it's simple for right now. That armature passes through a magnetic field that changes from 0.5 Tesla to 1.5 Tesla. That rotation takes 0.1 seconds. So think of that armature rotating through a certain rotation, like from here to here or something like that, a fraction of a rotation. That takes 0.1 seconds. The area, I'm telling you what the area of the coil, the armature is. It's 0.2 meters squared. You tell me what is the output voltage of that generator at this point in time. So once again, I'll give you a minute and then we'll talk a little bit. All right, it's been a minute, so let's go over this. So we're talking about a relationship between a changing magnetic field in a certain amount of time in a coil of wire, and we know the area of that coil of wire. So to find the relationship between all of these things, we know an equation that can tell us that relationship. It's Faraday's law. So Faraday's law in this is this relationship right here. The induced voltage in the coil of wire is equal to negative N, which is the number of turns in the coil, times the change of magnetic flux per unit time. So this combined is the rate of change of magnetic flux. I like to write down what I know first. I know that N is only 1, which is extremely unrealistic, but it's simple for this example. So for here, N equals 1 turn. Delta T, we're told, is 0.1 seconds. So I know that. The other thing I got to find in this equation, to find that, okay, I know that, but I got to find that, the change in magnetic flux. We know the change in magnetic flux is phi2 minus phi1, the flux at time 2 minus the flux at time 1. And the flux is just equal to BA, the magnetic field times the area of the coil. So we're going to take B2A2, flux at time 2 times the area of the armature at time 2, minus B1A1, the magnetic field at time 1 times the area at time 1, and then recognize the area is not changing. It's a constant 0.2 meters squared. So you can factor that out. And we got the area times B2 minus B1, the magnetic field strength at time 2 minus the magnetic field strength at time 1. If we look up here, it changes from this to that. From this to that. So this is the magnetic field strength at time 2, and that's the magnetic field strength at time 1. So we're going to end up taking 1.5 Tesla minus 0.5 Tesla. So that's what we do here. You plug in for the area, plug in for B2 and B1, and then you solve that. I made the numbers work out pretty nicely in this example. 1.5 Tesla minus 0.5 is just 1. 1 Tesla times 1 meters squared would be 1 Weber, but here we have 0.2 meters squared. So 1 Tesla times 0.2 meters squared is 0.2 Weber. So now I can plug that into my change of magnetic flux. So these numbers work out quite nicely. My induced voltage is negative 1 turn times 0.2 Webers divided by 0.1 seconds. And I can actually do that in my head, and so can you. 0.2 divided by 0.1 is 2. 2 times 1 is 2, and then take that times negative, so you get negative 2 volts. So the induced voltage here is just negative 2 volts.
Professor?
Yes.
To get Weber, is that just Tesla multiplied by meters squared?
That's
how
right.
that unit's okay.
Yep. Whenever you multiply Tesla times meters squared, you'll get Webers. So it's really important when you're calculating your area. It's really important when you plug it into this equation, you always need to have your area in meters squared. So be careful about that. As I recall, I think in the next problem set, there is a problem where you need to convert into meters squared. If you're getting here's a hint. Let's say the separate problem. Let's say you're given that the armature, the coil of wire, is a circle, and let's say that you're given that the radius of that circle is, I don't know, 30 centimeters or something like that. So you know how to calculate the area here. The area is pi r squared. But my recommendation, you don't have to do it this way, but my recommendation is to convert from centimeters to meters and then plug it into this calculation to find the area. So if you plug in 30 centimeters there, you're going to get the area in centimeters squared. And be careful, because 1 meter squared is not equal to 100 centimeters squared. 1 meter is equal to 100 centimeters. So just be careful when you do that conversion. The way to avoid converting meters squared to centimeters squared is just to do that conversion first. Convert from centimeters to meters first, and then calculate the area. That's a little hint that I think might help you on today's problem set. All right, good. Any other questions? All right. So we're going to move onward and talk some more about generators, increasingly realistic. So we'll talk about increasingly realistic generators today.